Today we're going to talk a little bit about solubility. So solubility is the amount of solute that can dissolve at a particular temperature. So we're going to talk about today that solubility is temperature dependent, and solubility is typically expressed in grams of solute per 100 grams of solvent. Okay, and we're going to do a lab where we express our solubilities in these terms. Okay, so a solution that's unsaturated is one that does not contain the maximum amount of solute, right? A saturated solution is one that contains all of the possible solute that can dissolve. And then a supersaturated solution, this is a little bit weird to think about, but a supersaturated solution is sort of a tenuous state where you actually have more dissolved than could dissolve. And so let's talk about what happens in each of these cases to maybe make this a little bit clear. So if we have an unsaturated solution, like I have shown down here, if you add solid to that, all that's going to happen is the solid is going to dissolve, okay, because an unsaturated solution can dissolve more solid. If you have a saturated solution and you add solid to that, that would be this case down here, what's going to happen is some of the solid molecules are going to go into solution, but at the same time, some of the ones that are in solution are going to become part of that solid. So overall, you're going to not dissolve any more solid than you had to start. Okay, a supersaturated solution might look like this. So if our solute is orange, it would be orange in color, and we have actually more dissolved than we should. But if you add a teeny bit more solid, we call this a seed crystal, what's going to happen is none of that is going to dissolve. All that's going to happen is some of what was dissolved is going to come back out of solution and join that precipitate. Okay, so those are the three different kinds of solutions in terms of solubility. Right, and we can plot this on a chart, which we're going to do in the lab. We're actually going to plot KNO3, which is the green line here. And you have this table in your notes as well, but it's in black and white. Okay, and what you can see is that for solids, for the most part, as you increase the temperature, which is to go this way on our little chart here, the solubility goes up. So as things get warmer, more solid dissolves. Okay, and you, in terms of what you should be able to do for this chart, you should be able to read this chart and figure out which thing would be more soluble at a given temperature based on the graph. So this is just reading X and Y axes, which I sort of expect that all of you can do. And we're going to plot these in class as well. Okay, so for solids, as I just talked about, as you dissolve a solid in liquid, the temperature as the temperature goes up, when you dissolve a solid in a liquid, the solubility also goes up, okay? So you should know this from your own experience. If you want to dissolve sugar in iced tea, that's a lot harder to do than to dissolve sugar in hot tea, for example. Now, gases, it's actually the opposite. So as temperature goes up for a gas, those gas molecules are going to be moving much, much, much faster. And so when you increase the temperature of a gas or a liquid that has a gas dissolved in it, the solubility actually goes down. And you should be able to think about this in terms of soda. That is probably the most common liquid that you know of that has gas dissolved in it. If you drink warm soda, as soon as it hits your tongue, bubbles come out a lot. And so that's because at that warm temperature, the gas is not as soluble, and when you give the liquid more surface area, the gas all comes out. Whereas if you drink cold soda, you notice the bubbles, but not nearly to the same extent that you do if it's warm. Okay, so for gases, as the temperature goes up, the solubility goes down. So they're the opposite of each other. Okay, and now we're going to talk about Henry's law. So we just finished a discussion of gases and all the different properties of gases. So we're not going to do any calculations with this, but I do want you to understand that when you have a gas that is at pretty low pressure, so this is at 1 atmospheres, then a certain amount of gas will be dissolved in solution. But if you have a higher pressure of gas in the area above the solution, that's going to force more molecules down into the solution to make them dissolve. So as the pressure goes up, the solubility of your gas also goes up, and that's Henry's law. So as pressure goes up, solubility goes up. Okay, so what we're going to spend most of our time talking about in this chapter is the solubility of salts and the solubility of solids. So this table here might look confusing. You don't need to memorize this table. You don't need to memorize any of this information, but you do need to know how to use the table. So the top half of the table is things that are generally soluble here, okay? And all of any salts that contain these ions are generally soluble with the following exceptions. Okay, so the first two don't have any exceptions, so that's easy. And then the second two groupings do have some exceptions. So for example, if you had sodium chloride, it would be soluble, but if you had silver chloride, because silver is one of the exceptions, it would be insoluble. So you just need to know how to read the table. And the bottom half of the table, some students get these confused because the bottom half is the opposite. So these are things that are generally insoluble unless they're paired with something that makes them soluble. So hydroxides are generally insoluble unless they're paired with lithium, sodium, potassium, or ammonium, for example. And you can see that these are the ones that are also up here. So there's no exceptions to when those ions are soluble. So even if they're paired with something that's down here, they would still be soluble. Okay, so we're going to do some practice with these, and hopefully you'll get a good sense of how to use this table. So let's take a look at some practices. So for these, you want to just state whether the salts are soluble or insoluble. So potassium sulfide. At the top of the table, it says that all potassium salts are soluble, so this one is going to be soluble. Calcium nitrate. The top of your chart here says that all nitrates are soluble, and there are no exceptions, so that one is going to be soluble. Lead chloride. Generally, chlorides are soluble. We're in the top part of the table here, but lead is one of the exceptions. So this one would be insoluble because lead chloride is not. It's one of the exceptions to chloride being soluble, so it would be insoluble. All right, sodium hydroxide. We could look in two different places for this one. The sodium is in the very top part here, and that's always soluble, and there's no exceptions, so you should know that sodium hydroxide is soluble. But you could also look at the hydroxide down here. So hydroxides are generally insoluble, except for the case of sodium. So sodium hydroxide still soluble. And then the last one is aluminum phosphate. And you can see at the bottom of the table, phosphates are generally insoluble. There are some exceptions here, but aluminum is not one of them. So aluminum phosphate would be insoluble. Now the last thing we're going to do with these is called precipitation reactions. Precipitation reactions are just double displacement reactions. So if you don't remember what that is, go back to chapter 8 and review the types of reactions. So this is just a double displacement reaction where one of the products is going to be a solid, so a precipitate. And that's one thing I should mention. A precipitate is the solid that forms in a reaction. A lot of students think of it as being a liquid because precipitation is like rain, but it's similar to precipitation in that the clouds get saturated and then the rain falls out. In our case, it's the solution gets saturated and a solid falls out. So the precipitate is going to be a solid. All right, so our problem is when solutions of silver nitrate and sodium chloride are mixed, a white solid forms. So we want to write the ionic and the net ionic equations for the reaction. So when we write an ionic equation, what we're going to do is write out all of the ions separately, because we now know that when we dissolve a salt in water, if it dissolves, it also dissociates and separates into its two different ions. So in this, if you don't remember your polyatomic ions, I will still give you the chart, but if you're not familiar with them, it's going to be very difficult for you to do these problems even with the chart. So you should go back and review those a little bit as well. All right. So silver nitrate is soluble. It tells us both of these things are in solution. So the two ions are going to be Ag plus, which is aqueous, and nitrate, which is NO3 minus, also aqueous. And then we also have chloride. So we have Na plus, which is aqueous, NCl minus, which is aqueous. Okay, and for all of those, I got those charges from the periodic table, or the one for nitrate is known, and you could look it up in the table if you needed it. Okay, so when all of these things are floating around in solution, they'll swap partners, and that's what a double displacement reaction is. So the silver was paired with nitrate. Now it's going to pair with the other thing that has a negative charge, which is the chloride. So that will be AgCl. For right now, I'm going to leave that state unwritten, so we haven't yet determined if it's a solid or if it's in solution. And then the other one would be sodium pairing up with nitrate, which would be NaNO3. Okay, so now let's check and find out if these are going to be soluble or not. So silver chloride, chloride is something that's generally soluble, but silver is one of the exceptions if you go back and look at your table. So that one is going to stay together as a solid, so we'll just put a little S there. All right. Sodium nitrate, sodium and nitrate are both things that are generally soluble. So that one would be aqueous, but because it's aqueous, we know it's going to separate into its ions. So it's just going to be Na plus aqueous plus NO3 aqueous. Okay, so this is our ionic equation. It's balanced. We have one of everything on each side. And so we're all done with the ionic equation, this part here. So the net ionic equation only wants to show what things change. So if you look at the equation that we have here, the nitrate and the sodium do not change from one side of the equation to the other. In both cases, we just have the ion there, and it's aqueous. So this is what we call a spectator ion. A spectator is similar to a spectator in sports. They're present, maybe they're cheering, but they aren't actually participating in the game. So these aren't part of our equation. So we're going to cross out the spectator ions, okay, and then just rewrite the equation with the things that do change. So silver starts out aqueous on the left in the reactants, and chloride starts out aqueous in the reactants, but then as the reaction progresses, they come together and form a solid, all right? So that is our net ionic equation. So a net ionic equation removes the spectator ions. Okay, so this is just one example of a precipitation reaction, but trust me, we're going to do many of them over the next week or so, and you'll get lots of practice and get good at it.